our next presenter. Our next presenter is Adam Abinales. And Adam Abinales, if for those who are not very familiar with him, is one of the pillars of the ASEP. He has been one of the past presidents and an incumbent director at the moment. And he has served in many committees of the association, like the Earthquake Quick Response Program, together with the PICE. And he is also an active officer of the Philippine Institute of Civil Engineers as president of the Makati chapter for this year. And he also served as a national director of PICE in 2012 to 2013. He's one of the leading consultants when it comes to structural engineering and, of course, retrofitting of structures. He's the principal of the Abinales Associates Engineers and Consultants. And, of course, for his academic background, he's graduate of BS in Civil Engineering for a long, long time ago. I will not mention the date. You might know his actual age at the moment. He also had a degree in Masters of Civil Engineering in structures. And to give you a simple introduction, he's one of the 75 Filipino outstanding civil engineers, as awarded by the Mapua Institute of Technology, now Mapua University. Ladies and gentlemen, friends, let's all welcome the legend when it comes to structural retrofitting to discuss this topic on retrofitting of existing structures, techniques, codes, and guidelines. Let's welcome Adam Abinales. Back to
Okay,
you, Adam.
thank you, Johnny. Thank you for that kind introduction. Um, you said one of the pillars. No, I think the pillars are in the likes of boss upping season. Anyway, thank you very much. So now I would be presenting to you and discuss to you the retrofitting of existing structures. So let me just share my PowerPoint. Oops. Ah, wait, wait. Okay, again, good afternoon, ladies and gentlemen. Well, of course, fellow engineers. Now, we are on the second topic, so I would be discussing retrofitting of existing concrete structures, techniques, codes, and guidelines. So let me present to you the outline of my presentation for this afternoon. So I have here to discuss about failure mechanism in concrete structures. Although some of these were already discussed by Doc Mac Mendoza in the first topic. And then, of course, some damages in concrete structures with infill walls. Then I would be presenting to you the retrofitting as a strategy, what and why. And then what are those retrofitting techniques that we can employ if we are going to do retrofitting of existing structures? Then what are the references, codes, and guidelines that we can refer to, use as reference in doing the retrofitting design? So let me talk about the failure mechanism in concrete structures. First, we have these failures of member level. So in the Philippines, most of our concrete structures, or rather most of the buildings here in the Philippines, are made of reinforced concrete. So in essence, we can uh, call most of these structures as uh, concrete moment frames. So you will have a lot of a possible flexural failure in columns. So you can see this in the photo here that you have the corner column in severely damaged, or I would say this is almost uh, not reusable, no, in terms of resisting the force. And then some other aspects of the flexural failure in column. Then we also have the shear failure in columns, wherein as you can see here, that the ties, no, as to the position of the reinforcement and how the reinforcement behave uh, as affected by this failure, you will see that there seems to be that this column will not be effective anymore. Now we have these short column and long column effects. When we say short column, this is a failure of column due to the crushing of concrete. And in some cases, you will see a lot of this, or this scenario would be very prevalent, no? When you have openings in a facade wherein you have the columns and then you have openings, say for example, windows, wherein that portion of the column which is unsupported will be considered a short column. Or when we say long column effect, the failure here is due to the buckling of the concrete. So as evidence here, as the short column effect this is a very classic case of failure in most concrete reinforced concrete frames. Then of course you have this damage to beam column joints. Then as you can see here, you have exposed reinforcement, but trying to look at this joint here, it seems that the joint, the longitudinal reinforcement in that joint have no sufficient or no transverse reinforcement. And then looking at this failure here at the joint, as well as this joint here, and then of course this cracking of the joint here, and this type of failure of the joint. Most concrete buildings in the Philippines are are provided with these masonry infill walls. Well, basically, I think we are very much well. Most Filipinos would like that their structure or their buildings would be made of reinforced concrete, and you have these very solid claddings, which is covering the building. And in some cases, we use concrete hollow blocks as masonry infill. Now, trying to understand the other type of failure is, of course, wherein you have your structure in total collapse. And this type of failure is considered to be a failure of structure as a whole. So trying to look at this photo here, and I'm sure you are very much familiar with this photo here. This is the Hyatt Terraces Hotel in the aftermath of the July 16, 1990 earthquake that hit Baguio City and other provinces in northern Luzon. And then on this photo here, this is a residential building that collapsed in the aftermath of the earthquake in Mindanao last October 2019. And this photo here is also another building in Cotabato. I think this is about a 6 or 7-story building that the building is considered to be in its collapse stage. Other observed failure modes, as I have mentioned a while ago, most concrete buildings here in the Philippines are cladded with infill walls. Now, the question here is this infill wall, no, would also tend to fail if, well, considering how we model and how we analyze our moment frame or the concrete frames, in most cases we do not actually model the infill walls. But depending on how these infill walls are connected to the frames, then these infill walls will also fail if there is no if they are not actually designed to resist the shear force that will be transferred due to the ground shaking. So most infill wall will fail due to inadequate shear strength. Sometimes most of the masonry walls used here are non-load bearing, or these walls would be out of plane flexural strength. As I have said, this is very common in the Philippines. So if you try to look at the failures in masonry infill RC frames, you could have something like a shear hinge damage mechanism resulting in the formation of a concrete wedge. And this can be attributed to the strut action of the infill walls. So trying to, sorry. So looking at this frame here, so normally if you are really going to model your infill wall as part of your moment frame, then they should be modeled as a strut. But if you do not, do that, and then the connection of the walls to the frame would be something that it will tend to receive forces from the earthquake, then definitely these walls will fail. Then, and as I have said, this is very common in almost all buildings in the Philippines. Before the introduction of the modern seismic design provisions in the mid 70s. Now, if we try to recall the first national structural code published in the Philippines was in 1972. Or you could have a local damage or failure of beam connections or beam column connections, which is the leading cause of building failure and collapse. Now, we have seen a lot of this during the Bohol earthquake, the Negros Oriental earthquake, and even the past earthquake, no, wherein a simple residential dwellings, one story or two story, wherein they have these something like, they call it a silong or a lower ground, wherein most of these failures are very, very prevalent. Or you have, now this is another photo. Actually, this photo here is a photo taken on one of the collapsed or rather damaged buildings in Negros Oriental earthquake, wherein, as you can see, the column is already detached from the superstructure or from the structure itself. So structures with an open bottom story have significant concentration of the drift, and the structural damage becomes considerable. So this type of frame, no, RC frames with infill walls, regarded as an earthquake risk, not only in the Philippines, but also in other countries like in New Zealand. Let me talk about a case of failure of masonry infill RC frame. Looking at this photo here on the right, you have a residential building structure which failed ground floor masonry infill and columns, even if the building is composed of these infill walls and columns. The structure nevertheless still failed. So maybe for reasons that the material used are substandard, or this building was constructed without the benefit of something like a professional design, or basically it was just built, no, without the proper, no, documents that it should be standing as such as there, or maybe you have a case of a masonry infill apparently that got disconnected from the concrete frame. Well, I think this is one thing that most engineers or most constructors should look into, because if the infill walls are not properly connected, but providing a space not to make the walls too rigid or too stiff, so that it will not affect the behavior of the concrete frame. Inadequate connection between the infill and the concrete frame. Or there is a case of what we call as a weak beam column joint, which is very apparent. Or you can have a case of a masonry infill RC frame, very massive on the upper floor with bare concrete frame on the ground floor. So this is something like a case of a soft story. Or you can have a case of a damaged two-story. This one is actually a barangay hall in Negros Oriental earthquake with masonry infill concrete frame. So trying to look at this, the connection of this floor here to that of this column here at that particular joint, there is inadequate connection between the masonry and the beams. Actually, there are supposed to be some walls here, but I think they have been torn down. And the beam and columns and the joints of this column to that frame there, with sparsely spaced lateral ties, as you can see here at the beam column joints. If we try to understand the behavior of masonry infill RC frames, like for example in the case of and that of the unreinforced masonry structure, well, as a rule of thumb, no, the concrete frame should be able to withstand a lateral drift of about 1.5 to 2% before the beam column joint or column failure, or the maximum stress of the unreinforced masonry is reached at a drift angle of approximately 0.3% only. So in the case of unreinforced masonry, may be expected to fail before the concrete frame does. Reality check, similar methods of building construction made of RC frames with concrete hollow blocks as masonry infill are predominantly very common in the Philippines. We may ask, can these damaged structures be restored? The quick answer could be yes. Now we talk about retrofitting as a strategy. If our answer there is yes in the previous slide, then meaning we can still restore, no, the building. Well, of course, retrofitting or restoration of a damaged building would be subjected to a very thorough, detailed evaluation before you decide that a retrofitting would be your strategy. I have seen a lot of questions in the previous presentation wherein they have been talking about or asking about the retrofitting. So maybe I hope that I would be able to answer some of these questions in the first presentation. Now, why do we need to retrofit? And what is retrofitting all about? Let me define, no, taken from the Engineering Principles and Practices, the FEMA. Retrofitting is any change made to an existing structure to reduce or eliminate the possibility of damage to that structure from extreme winds, earthquakes, flooding, landslides, or other hazards. Now, our presentation, no, the previous presentation and my presentation would focus on the effect of earthquakes or the action of earthquakes on our structure, because in most cases, no, we would like our structure to be able to withstand the damaging effect of earthquakes. What are the advantages of retrofitting? All structural problems have more than one technical solution. So in retrofitting, we can, I would say the engineer would have a lot of choices. But of course, the strategy would depend on how we go about the design and be able to satisfy other requirements, no, as far as retrofitting requirement is concerned. And final selection will ultimately rest upon an economic evaluation of the alternatives. You know, if you think of, say, if you're doing a retrofit or detailed evaluation of an existing structure, and eventually you will be doing a retrofitting, this is one important aspect that you have to consider, the economic evaluation of the alternatives. Well, there seems to be I would say in as a industry practice or industry standard, that if the cost of retrofitting would be about 60% of the cost of a new construction, then you may decide that you do not push retrofitting anymore, but rather demolish the entire building and then put up a new one. But of course, it will all depend on how you really evaluate your design. So why retrofitting? When do we consider that we really need to retrofit structure? It says here that the damaged or deteriorated structures, you can still retrofit. But if there are cases wherein your structure would have reached that unrepairable state, then you will have to think twice about doing the retrofitting. Or you have an aged structures not compliant with the current code. There was a question before during the first presentation that when do you consider evaluating or retrofitting an aged structure? Now, um, actually, in the Philippine Building Act, which is still pending at the Congress at the moment, there is a provision there in that particular bill that any structure which has been more than 15 years, meaning that the professional liability of the engineer of record of that particular building, the building would be subjected to mandatory structural evaluation. But as to the retrofitting, definitely, if it is just, say, barely 15 years or over 15 years, then the retrofitting will be dependent on the outcome of the evaluation. But if the building, say, for example, about more than 20 or 30 years, and then that building was designed based on the previous code, and then now we have a current code, then most probably, or maybe you would be thinking about retrofitting of that particular age building. Or you will have a structure that serves new occupancy, meaning, say, for example, you have an existing building, and then the occupancy, say, before it was, say, for example, it's just a simply standard building, and then you are converting it to be a structure that will be accommodating a bigger life load, then you are practically changing the occupancy. So in that case, there would be a change in the loading. Or if you have a structure wherein you expand it vertically, then you will be supporting additional loads, then obviously you will have to do retrofitting of the lower floors. Or your structure has some known deficiencies in during the construction. Uh, I would like to note that this really happens because we have experienced a lot of, or rather, we have some projects wherein we see an existing, or rather, a newly constructed buildings which have deficiencies while these buildings are being constructed. So obviously, you will have to do some retrofitting. Or you will have some design deficiency. When you talk about design deficiency, it depends on this this may happen, no? When the building is already constructed, and then you have all those design, and then during the early subversibility of that building, there are some manifestation of some cracks or distress, then there would be a cloud of doubt of having design deficiency for that particular building. So in that case, you will have to do a detailed evaluation. So in your evaluation, you might find out that the potential to the actual strength, you have a deficiency. The potential to the actual serviceability, you have an issue, or something like you have not met the performance level objective. As we all know, as far as the code or the NSCP 2015 or the previous NSCP codes edition, life safety is the minimum uh, code requirement set as the performance level objective. Let me just present to you this a video.
Earthquakes have always been a terrifying phenomenon, and they've become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. Why do buildings collapse in an earthquake, and how can it be prevented? If you've watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently, or even splitting apart. But that's not really how it works. For one thing, most buildings are not located right on a fault line, and the shifting tectonic plates go much deeper than building foundations. So what's actually going on? In fact, the reality of earthquakes and their effect on buildings is a bit more complicated. To make sense of it, architects and engineers use models, like a two-dimensional array of lines representing columns and beams, or a single line lollipop with circles representing the building's mass. Even when simplified to this degree, these models can be quite useful, as predicting a building's response to an earthquake is primarily a matter of physics. Most collapses that occur during earthquakes aren't actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to cause a certain amount of displacement. Along with the building's material type and the shape of its columns, stiffness is largely a matter of height. Shorter buildings tend to be stiffer and shift less, while taller buildings are more flexible. You might think that the solution is to build shorter buildings so that they shift as little as possible. But the 1985 Mexico City earthquake is a good example of why that's not the case. During the quake, many buildings between 6 and 15 stories tall collapsed. What's strange is that while shorter buildings nearby did keep standing, buildings taller than 15 stories were also less damaged. And the mid-sized buildings that collapsed were observed shaking far more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency. In an oscillating system, a frequency is how many back and forth movement cycles occur within a second. This is the inverse of the period, which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around. Increasing a building's mass slows down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So in the equation representing their relationship, stiffness and natural frequency are proportional to one another, while mass and natural frequency are inversely proportional. What happened in Mexico City was an effect called resonance, where the frequency of the earthquake's seismic waves happened to match the natural frequency of the mid-sized buildings. Like a well-timed push on a swing set, each additional seismic wave amplified the building's vibration in its current direction, causing it to swing even further back, and so on, eventually reaching a far greater extent than the initial displacement. Today, engineers work with geologists and seismologists to predict the frequency of earthquake motions at building sites in order to prevent resonance-induced collapses, taking into account factors such as soil type and fault type, as well as data from previous quakes. Low frequencies of motion will cause more damage to taller and more flexible buildings, while high frequencies of motion pose more threat to structures that are shorter and stiffer. Engineers have also devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibrations. In the end, it's not the sturdiest buildings that will remain standing, but the smartest ones.
Okay, so basically, when we talk about retrofitting, and by the way, I would like to acknowledge Dr. Andy Oreta for that video, because I took that video from one of his presentation. Okay, so basically, when we talk about retrofitting, we are focusing more on the structure to be earthquake resistant. So if you have a building, and then we subject it to the usual gravity loads, and then we analyze it for lateral forces like wind, and of course the excitation of the ground. Now the building itself, no, would be able to dissipate, no, say for that ground motion, that seismic energy from the earthquake would be dissipated by the structure itself. As we all know that the building itself has its damping characteristic, and there's a certain percentage of that building to be able to dissipate the energy from the ground motion or ground shaking. So that's why where we design our structural or the building or the structural members of the building, wherein we have to satisfy strength and of course ductility. Definitely, when we talk about ductility, we see to it that we be able to satisfy the requirement of the code as far as seismic detailing is concerned. And then in our design of the structure, we deal with these other properties of the structure. We look at the dimensions of the floor to floor, the dimensions of the base, and the number of structural elements to be used, the columns, the shear walls, and so on. And then we must be able to design it so that we'll be able to satisfy, no, the requirement for the deformation within the elastic range. And then, of course, as we push the structure further, then we must be able to satisfy the deformation capacity in the plastic range. That is where the ductility will come in. So trying to look at this graph here, the force and the displacement curve. So within the elastic range, we design our structure within the elastic range, and that is the premise of the code. Now, if we try to push further, and then we for the structure to be able to sustain, no, exert forces due to base shear or due to earthquake, then the structure must be able to have that capacity to absorb further deformation if the structure is properly designed, no, for ductility. So in that case, the structure should be able to resist or to sustain that large deformations, and we must be able to, if ever, the structural damage would be very minimal. Now, when we talk about earthquake resistant, we expect that the building or the structure will still have would still be able to sustain some damage, but not to the point that the damage would be irreparable. Because otherwise, if there is really if that building would be subjected to a strong earthquake, then you might end up doing a costly repair. So this is the this graph here wherein we try to define the performance level objective. So as we'll know that for our structure to be able to sustain large deformation and then satisfy the life safety requirement, then we can go beyond this point. But definitely, it really depends on the uh, the earthquake, no, motion that would be subjected to your structure. Now, uh, when we do retrofitting, what are the strategies? No, actually, the advantages. Well, basically, it completes the load path. No? In some cases, when if you find some issues about uh, the load path, the load pattern of the lateral force resisting elements, then you will be able to eliminate or reduce the potential structural irregularity. So what you see on the right side of the slide, you have this table from in the NSCP 2015, in particular tables 208-9 and 208-10, which discuss about the vertical structural irregularity and horizontal structural irregularities respectively. So when you talk about vertical irregularity, you have a case of stiffness irregularity and commonly known as soft story, or you have a mass irregularity, or you have something like a vertical geometric irregularity, or you have a case of in-plane discontinuity in the vertical lateral force resisting element, or discontinuity in capacity, or otherwise termed as weak story. In the case of horizontal irregularity, you have torsional irregularity, then you have a reentrant corner, then you might have a diaphragm discontinuity, or out of plane offsets irregularity, or non-parallel system. So if we try to understand these irregularities, so you can have these example illustrations of these irregularities. So when we talk about reentrant, you have something, these shapes of your building plan. And also this kind of opening in a particular, or rather in the floors of the building. When you talk about vertical irregularities, you have something like soft stories here, or something soft stories here or here, or you can have some a very large setback, wherein this is considered to be a critical point, or you have a very a top-heavy structure, or a structure on a hillside, or something like a two adjacent buildings wherein you do not observe seismic gap, then you will have a case of pounding because of the different uh, behavior of this building when subjected to ground shaking. Now, let me just show you this video. Actually, this is a case just showing you one of irregularity that needs to be well, look into. No? So you have a case of pounding because you have a U-shaped building, and then of course this is very common in public school buildings here in the Philippines using U-plan. And then of course if you have this case, then it's better that you have a seismic gap at this joint. Basically, retrofitting will strengthen the structure. Then I think no doubt about it. No, that is the main objective of retrofitting. Whether you do it localized member retrofit, or you do the global retrofitting. And in that case, you reduce the earthquake demand, and you try to compare the demand vis-a-vis the capacity of the structural elements. It improves sustainability and energy performance of the building. Say, for example, if you are using some passive devices or passive systems, wherein you use, like a base isolation or a damper or a vibration control device, then you would be able to reduce the vibration of the structure, especially if the structure would be susceptible to large vibrations. So in that case, if you have vibration control, looking at this curve here where you have the height against the displacement of the structure, if you do not have a vibration control, then you expect that the structure would behave something like this, wherein you have a very large deformation. But if you put some controlling vibration control device, then you will be able to reduce. So in that case, you are actually improving the energy, the performance of this structure in terms of energy dissipation. Or if you have some structure with the damping device or system, then you would be able to reduce the seismic demand. So retrofitting an existing building can oftentimes be more cost-effective than building a new facility. Since buildings consume a significant amount of energy, if you try to imagine and try to look at the sustainability in building construction, 40% of the nation's total energy consumption is being utilized, no, for building construction, especially or even occupancy, no, for especially if you talk about heating and cooling, that's almost about 32%. Nowadays, we have been talking about green building, and I think as a structural engineer, we also have our role, how we make our building to be compliant, no, as a green building certified. And because existing buildings comprise the largest segment of the built environment, it is important to initiate energy conservation retrofits to reduce energy consumption and the cost of heating, cooling, and lighting buildings. But conserving energy is not the only reason for retrofitting existing buildings. Note, again, you have to consider the main aspect, why do we do retrofitting? And that is depending on the outcome of your detailed evaluation. So the goal should be to create a high-performance building by applying the integrated whole building design process to the project during the planning phase that ensures all key design objectives are met. So trying to look at this diagram here, you have a structure capacity and the displacement demand after retrofitting. So this is the graph when the building is not yet being retrofitted or is not retrofitted. Then you have this drift demand at this point. But when you do some retrofitting, either you do it system strengthening or element strengthening, there would be a substantial drop, no, of the of this curve down to this curve, no, especially in terms of the drift, you will be able to have a significant reduction of the, or rather, yeah, reduced drift demand to this line here. But of course, this is in the case of system. But if you are only doing an element strengthening, the drift demand would slightly be lowered, no, to the shifted to the left, not exactly. I would say significant reduction of the drift requirement, but what I'm trying to say here that there is other system or other alternative wherein you can do the retrofitting in terms of the whole structure. So this is basically the key philosophy of seismic retrofitting. It's either you do element strengthening or you do the system strengthening, or you do the combination of both. So let me talk about retrofitting techniques. So now we laid down the key philosophy of seismic retrofitting. So what are the possible techniques that we can employ? Let me classify retrofitting techniques. First, you have the local level, or in a sense, we have the element strengthening. And the second is the global level, uh, retrofitting the entire structure, and this is the system strengthening. So let me show you this flow chart. Retrofitting techniques can be classified into two. Either you do global, or you do local, or you do both, or a combination of both global and local. For the local, we have strengthening of the beam or the slab. We have the strengthening of the columns. You have the strengthening of the beam column joints or strengthening of the footings. For global, we may add infill walls, we may add shear walls, we may add wing walls, or we can do thickening of shear walls. Now you will note here that I have a line here also in, under the local, because if the thickening of the walls would be covered only to some floors, then it should be localized. But if the thickening of the shear walls would be all throughout the height of the building, then it would be global. Or you can do add bracings, or simply you reduce the mass, the weight of the structure, or you install damper, or you install base isolators. Now, if you try to look at this chart here, weight mass reduction I would say has not something to do with the stiffness, not changing the stiffness of the structure. So basically, for all other strengthening techniques here, except for the weight mass reduction, this may not change the stiffness of the existing structure, but the rest will definitely change the stiffness of the structure. So let me just focus to each of these techniques. Strengthening. Jacketing is one of the most frequently used traditional techniques to strengthen RC members. So you have a case in this photo here, strengthening this frame here, or that frame here, or that frame here, or this column here. Strengthening of RC column is needed when the load carried by the column is increased due to maybe increase in the number of floors or design deficiency. The compressive strength of the concrete or the percent and types of reinforcement are not according to the code. You might ask, does this really happen? Yes, because we have seen a lot of, well, in my personal professional practice, we are doing some review of design of other engineer of record, and sadly, we find some case wherein the designer have this kind of issue. Or the inclination of the column is more than the allowable. Well, as we all know, the column should be laid vertical, no? It should be vertically aligned. But if there will be some displacement or the deformation of the structure, then there is a tendency of the column to be out of plumb. So, of course, like in the case of Tower of Pisa, although that is very classic, and even if it is inclined, still it remained as it is. Or there is a settlement in the foundation which is more than the allowable. What are the major techniques of strengthening? Now, we have the traditional. When we talk about traditional, we have the concrete jacketing and we have the steel jacketing, or simply we call this using externally bonded steel plates. Now, the alternative would be post-tensioning, or you have a fiber-reinforced polymer wrapping, no? Of course, we call this FP wrap. Concrete jacketing. I would say concrete jacketing would be inexpensive, relatively. But increasing the strength of the structural member, no, you use jacketing, you increase the stiffness, but you increase the seismic wave, no? So that is the downside, okay? Even if you have that, you know, say for example, the original is 0.3 by 0.3 column and then you make it 60 by 60 column just to satisfy the demand, then definitely you're adding seismic wave. So that is the drawback. For steel jacketing, same as in the case of concrete, it is inexpensive. Well, substantially, there would be an increase in the weight because of the weight of the steel that will be added to the element. The alternative is either you do post-tensioning. Now, post-tensioning is a method of retrofitting or strengthening concrete or other materials with high-strength steel strands or bars, typically known as the tendons. Of course, as you can see on this photo here, these are the tendons which are placed outside the face of the girder. Similar to this photo here on the right in the building, wherein you have these beams, no, a series of beams which are all uh, retrofitted or strengthened using post-tension wires or tendons. The application of post-tensioning may include office, apartment buildings, parking structures, slab on ground, bridges, sports stadium, rock and soil anchors, and water tanks. As you can see on the photo, so you have this line of the post-tensioning here, no, for the slab, and then this for tanks or big silos, wherein you have these post-tensioning here. Also in bridges. In many cases, post-tensioning allows construction that would otherwise be impossible due to maybe site constraints or architectural requirements. But of course, if the ceiling are exposed, then you can see the structural elements. Then definitely you can do the post tensioning here. But if you have a closed ceiling building, then that would be a big issue about architectural. But definitely, you can still do the post-tensioning strengthening, but you will be doing a lot of retrofitting works. Now, what you see here is a post-tensioning applied to water pipes. Now, FRP, wrapping. FRP, as we all know, is a system which is composed of composite materials made of fibers and polymeric resin. Now, when we talk about fibers, you can have carbon, you can have glass, or you can have aramid. And the resin, the polymeric resin that you can use epoxy, vinyl ester, or polyester. And with this composite material, you expect that you are creating the FRP, no, by combining high-strength thread-like fibers with the polymer or resin material, and the result is a rigid material that is high-strength yet lightweight. The fibers in the material give the material all of its strength and stiffness characteristics, while the polymer holds the fiber in alignment. So this is the result of the fiber. Now, what you can see here are some illustration of six structures that were fiber wrapped. Say, for example, you have these piers of a bridge, wherein you have series of columns here, and then they apply this retrofitting, or rather this strengthening using FRP, and now this is the finished job. Another case wherein you have this slender columns here, so trying to increase its flexural and shear capacities, then you have this wrapping, and then now this is the completed retrofitting work. Also here, then applying the FRP, and now you have the finished retrofitting work using FRP. In buildings, say you have a slab, and then you try to look at, do some retrofitting of this particular section of the slab, or maybe in the case of wherein there is an increased live load here in this area here, and then you can apply retrofitting here. Or maybe this could be along the line of the beam. It really depends, no? Actually, we have a case of this one wherein we have a multi-purpose court, wherein we have to do retrofitting of the slab because the underneath of the food court, or rather the multi-purpose court, there is a cistern. Or in pipes, no? You can also do this retrofitting inside the pipes. Okay, so that is all about those traditional and alternative, no, applied to strengthening of the beams, strengthening of the columns, strengthening of the joints, and then you apply these techniques. Now, what about strengthening the footings? Well, basically, you can do it either you have a concrete or steel jacketing. You can still do it using FRP wrapping, or there are cases wherein you have to intervene, no, and then especially under the foundation, and that is doing the underpinning. Or you can do the combination of both jacketing or wrapping and then underpinning. Now let me just show you some of the photos which you can do for strengthening of the footings. So this is a procedure wherein you can do the strengthening of the footings. So on the slide one, you have this exposed columns, and then of course the footing. Just imagine that portion here, which is only the footing of that column, and then you lay down your reinforcement, and then put all the rebars, and then the cage, and then pour the concrete. Or underpinning, you can do, say, actually there are a lot of methods or strategies, no, for doing the underpinning of structures. So either you use a drilled piling combined with the needle beams, or you can do exterior inclined piling, no, as you can see on item 2, or rather in figure 2. Or you do the chemical injection using polymers, no? Or in number 4, you can do micropiling or micropiles, no? The use of micropiles. And then in number 5, you do some soil or in situ stabilization. This is what we know as a ground improvement, no? Wherein you want to increase the bearing capacity of the underlying soil. So sometimes you can do it. Of course, if you have an existing building, then you can only do it either you do jet grouting or soil cement column. Now, what about strengthening of masonry infill or shear walls? No, basically, you just do some use of the spray-on materials such as engineered cementitious composites. So the process would be something like this. You have to expose the reinforcement because you want to, basically, if you have a crack here, and then try to get the influence area of this crack or damaged portion of the wall, and then you try to expose and then clean everything here. Then you do the application of the cementitious material, either by pressurized, what you call this, spray, no? Pressure jet of concreting. Or spray concrete of concreting to restore, no, the damaged portion of the wall. Now, let's go to the global. retrofitting schemes. Now, this global retrofitting tend to alter the behavior of the entire structure. So whatever it is, no, any of these techniques, that would be the effect. So if you try to, and this happens because there is a change in the load path. No, as I have mentioned a while ago, system strengthening will definitely change the load path, and it will reduce the seismic effects of the structure. The objectives of global level retrofitting is to increase seismic resistance, resulting to reducing seismic demand. Now, let me go each of these global level retrofit techniques one by one. Adding infill walls. The share of the seismic load is taken by the infill from the concrete frame. If the wall, or this infill wall, are so connected to the frame that it will affect the behavior of the frame, then make sure that you have a very strong, a good connection, because infill must be strong enough to absorb the seismic load. Adding shear walls. The share of the seismic load is taken by the shear wall from the concrete frame. Now, let's say, for example, here that you have this shear wall here that you have to introduce. Now, what you can see on the lower left portion of the slide is this colored green wall, wherein these are originally not present there. Originally, they are the same as the other base, wherein you have the wall opening. The wall opening where you have the windows. This is actually a three-story building which I have taken a photo in Taiwan when we visited there during the Tainan earthquake, after the Tainan earthquake rather, wherein this building were this base of this building were converted into shear wall, and this building performed well, no, during the Tainan earthquake, because that Tainan earthquake, this building was already there. Well, I would say that this building was damaged in the previous earthquake before. Adding wing wall. Well, this is very common in institutional structures like churches, wherein you have these wing walls here added to the frame, and these wing walls will take the share of the seismic load in the direction where they are added. Thickening of the shear wall. No? So basically, the share of the seismic load is taken by the thickened shear walls from the building frame applied throughout the building height. If the thickening of the shear wall will only happen not throughout the height, the building height, then it would be local. So the effect would be local. Now, let me go to the adding bracings. The share of the seismic load is taken by the bracings. So what is the effect? No? It will reduce the drift demand, can be placed either interior or exterior of the system, or these bracings could be post-tension, especially if you are using some tubular sections of the bracing. Then there are some introduced post-tensioning inside that tubular sections. Then you can do post-tensioning. The lower photo here is an existing building wherein the exterior facade of that building were strengthened using this bracing. No? In this case, you have the cross bracing. In this case, you have what we call as a chevron type bracing. Or either you have BRB, no? So same thing, wherein you have this photo here where the BRB are introduced. And I think what is a good thing about BRB is it is used for those buildings wherein you have this situation of weak column, strong beam failure mechanism. Weight or mass reduction. Well, basically, this is a case wherein you have a very top-heavy or upper floor to reduce seismic demand. Or sometimes there are buildings where you have a storage area, no, in the upper floors, and that you have to move them to the lower floor or to the ground floor, no. Ground floor, assuming that there is no basement. Now, let me proceed to the I would say, the introduction of passive systems or isolation, something like controlling the vibration of the building, or decoupling the superstructure from the substructure. So either you use dampers or you use base isolators. Now, typically when we talk about dampers, actually it is more of vibration control devices. So let me just give you a difference. When do you use vibration control devices, and when do you use base isolators? As you can see on this graph, this is a graph, no, wherein the ordinate, you have the height of the building, and then you have the dimension of the base. No? So as you can see here, on the green shaded portion of the graph, you can utilize base isolation. Well, obviously, as you go wider, no, you can increase the height of the application of the base isolation. But beyond that point, say about 80 meters, well, apparently you can say that you cannot use any more base isolation. But obviously, for a building height beyond this point, no, then you can use vibration control devices. That's why in tall buildings, in high-rise buildings, vibration control devices are very common rather than using the base isolation. So this is the height versus base dimension curve for structures having a period of 1.5 seconds, 1.5 seconds. So installing dampers as a vibration control device, no, the effect would be, if you have a building without these dampers, then definitely if you are at this particular floor or level of the building, then you expect that the vibrations of the building would be very excessive, not to the point that you cannot withstand or the shaking because of the ground movement. Then there is a tendency, if all the furnitures, all the all those furnishings in that particular floor would fall on you. But if you have dampers, then the vibration would be significantly reduced. Then obviously, if you are a tenant or occupant of that floor in that building, then you expect that as if you do not feel the shaking of the ground. Now, in terms of, say, looking at the height to the displacement of the building, so I think I have already discussed this a while ago. So if you have vibration control, then you expect that the displacement is reduced significantly. And then in terms of the shear force, the seismic demand is significantly reduced also. Because for reasons that the dampers would be able to dissipate that seismic energy from the ground shaking, because dampers have this function. What dampers can do? Dampers directly provide additional damping to the structure in the form of these discrete devices. Dampers have been designed to provide up to 50% of critical damping for many structures or even new structures. Dampers are introduced to reduce or eliminate structural yielding and architectural damage. What are the advantages of dampers then? So again, let me go back to the figure presented a while ago. So you have this building, and then you have these loadings, the wind, and the size and the ground shaking, and then you have the seismic energy which is being transferred to the structure. But basically, because of the inherent damping characteristic of the building, based on the proportion of the elements, the energy would be dissipated by the structure to a certain amount. But if you introduce dampers, then definitely that other seismic energy would be further dissipated by the dampers. So dampers would reduce energy transmitted to the structural members, and it reduces amplitude and vibration of the period of the vibration. Then in effect, the forces and demand would be reduced. So what happens if the building has dampers? So going back to the graph before, then you have the force and the displacement curve, wherein you design your building for within the code, within the elastic range, and then you know for a fact that you still have that ductility of the structure of the elements. It can absorb further the deformation. But if you introduce dampers, seismic energy dissipated by the structure, then definitely the structure would be subjected to small deformations, minimal structural damage, or none or almost slight repairs after an earthquake, because the remaining input energy is dissipated by the dampers without suffering damage. So let me show you some configuration of dampers. This is one dampers installed as diagonal braces, or dampers installed as a chevron brace, no, something like this, okay, wherein these are the dampers, or dampers installed in toggle brace. It could be outer frame, meaning you can put the dampers on the facade or the external facade of the building, although you may see that it would have an architectural aesthetic effect, no? Because practically you're covering the structure already with these devices, or something like this. Or it could be dampers in toggle brace, which is inside the building, no, or built-in frame. Now, let me just show you a video, no, of a structure without dampers and with dampers. Now, I personally took this photo of this video when I was in Japan, in which I visited a factory or a company manufacturing dampers. So you see the effect, how dampers would really reduce the deformation or the displacement of the building, as well as the seismic force. Now, let me talk about isolators. Now, I'm almost on the last part of my presentation. So principles of base isolation is that the structure is designed to remain elastic under reduced actions. The formations are concentrated only in the seismic devices, and that I'm referring to the base isolators. What are the advantages? Base isolators, again, reduce seismic demand. Base isolators raise both a structure's seismic performance and its seismic sustainability considerably. Base isolators lower inertial forces in the structure. They limit interstory drift, thus causing no damage, almost no damage to non-structural elements. Base isolators reduce perception of shaking. You know, if you are inside a building which has base isolators, actually I have heard as a personal, a personal experience of a friend wherein he is staying in a building which is base isolated. Everyone felt the earthquake, but those people in that building with base isolators, they didn't feel the ground shaking, because that is the perception. Base isolators promote immediate occupancy of the structure after the event. If there are advantages, then there are disadvantages. Base isolators can be an expensive solution. Contrary to popular belief, based on base isolation, it does not make a building earthquake-proof. Well, this is something like a debatable I would say, statement or phrase about earthquake-proof structure. Whether I have been talking about seismic retrofitting and I only use the term earthquake resistant, and I do not say that I do not use the term earthquake proof. So base isolators, if you use as retrofitting, because you might think, how can you retrofit a building using base isolators if it's already existing? Because in almost all cases, you can actually use base isolators when you are starting a new building. So but basically we can do base isolation for existing building. So say for example, you have a column to be cut. Definitely you have to cut the column. And then you place the support and the beams, no? Before you cut the column. So you have this mechanism here for you to be able to jack the building, no? I'm talking about all the columns in a particular floor, and normally you put the cutting of the column, if you want to base isolate it, is at the ground floor, okay? Or if you have a basement, then you look at the basement. Then once you put these supports for all the columns that you're going to cut, then you stress the beams and load the vertical jacks, because definitely once you cut the columns, then the jack, the supports, the jacks will carry the entire structure. So what happens then? You cut the column using diamond wire saw. You can do it. Then you complete the cutting and then grout the saw plates, no, as part of the mechanism of the jacks, and then you place the isolator. I think there is one paper during the AIC last year that a building, a hospital in Turkey was retrofitted using base isolators. So as a retrofitting, you can see these actual photos. So this is how it will look like when you have a column which is base isolated and the column is cut at this particular level, and as well as was this one. So you see, no, you see it can be done. No, it is not impossible. Now let me just show you this video, the effect of base isolation. So again, I took this video when I was in Japan. That company also producing or manufacturing base isolators. Okay. So base isolators plus dampers, when you combine it as retrofitting, it is also possible because viscous dampers acting in parallel with the isolators to increase the energy dissipation. When I was, when I visited Japan last year, no, sometime in October, I visited another company there, and their building is base isolated, and I went to the basement of that building and I see the combination of these base isolators with dampers. So you could just imagine, no? Maybe they are showcasing that building with these base isolators and dampers. Okay, so let me now refer you to the codes and standards. No, well, basically, one of the questions raised before is there's no such thing as retrofit, a code or standards or anything about retrofitting in the NSCP. Yes, you are right. No, there's no such thing. But let me just walk you through. In designing the choice of retrofitting techniques, before you go into the design, no, first you have an efficient and integrated load path. No, make sure that you will be able to really analyze your structure and identify this. Then you think about the strengthening and stiffening schemes. No, you don't think of one technique or two techniques. You have to think of all possible strengthening techniques. In fact, when we did some project for one government agency, we have to prepare 3 schemes. And that is the minimum requirement of that agency. Then when you do the analysis, You identify all the possible failure modes. All of these things you will be able to find out in your evaluation as presented by Doc Mac. Then you look at the increasing the deformation capacity of the members, no? Because that is your uh, uh, goal in retrofitting, and reducing the force demands in the members. So basically, these are the factors that you have to think of. And then, obviously, uh, you must consider also the aesthetic, no? Appearance of the structure. But if there are cases wherein you cannot really avoid putting all these retrofitting devices, then so be it, that the aesthetic would be compromised. No? Make sure that it can be easily constructed, or it is workable, or maybe is the technology available, no, locally available. But of course, in the Philippines, although we don't have some big factories here or shops here, wherein other tech devices are available, then we have neighboring countries in the ASEAN region where we can source this technology. Of course, you have to consider the cost, and you decide on the final retrofitting scheme. So, do we have a code? Are there available code? NSCP is our structural code, 2015. Section 101. There is one Section 101.4, alternative system. The provision of this code are not intended to prevent the use of any material, alternative design, or method of construction not specifically prescribed by this code. Although it is not explicitly discussed in the code, but we have this. Doc Mac Mendoza presented some codes, no, which are not, of course, part of the code as prescribed in this NSCP. But trying to look at the statement here, this is open-ended. So meaning you can use a reference standard or a model code where you can use, provided that is permitted and authorized by the building official. So going further, any system you can use. You can use dampers, you can use isolation, you can use whatever method, no, a combination based on this particular section of the NSCP 2015. Section 208, no, on earthquake loads. As to the procedure, the alternative earthquake load procedure, you are allowed to use alternative procedure. Actually, as long as you know that procedure. Now, there is a question, of course, that when we design our structure, we always design it using the code. No, it is code-based design. But if there is a need that you have to go further code-based design, especially in high-rise buildings, then definitely you have to use alternative procedure like performance-based. Also, in Section 208, there is these alternative procedures also discussed, alternative lateral force procedure using rational analysis based on well-established principles of mechanics may be used in lieu of those prescribed in these provisions. And in the same section, you have 208.4.8.4.2 on seismic isolation. Seismic isolation, energy dissipation, and damping systems may be used in the design and analysis of structures when approved by the building official and when spatial detailing is used to provide results equivalent to those obtained by the use of conventional structural system. So I would say that these provisions of the NSCP would give a hand, no, the structural engineer. But I would say that the structural engineer must be, no, knowledgeable enough on these aspects of alternative procedure. you really have to understand, fully understand the principle behind this. Okay. We have this ATC, that's 14, which is, well, basically, no, this is a publication created a concept of screening buildings for potential hazard. Of course, this is covered by the evaluation as presented by Doc Mac Mendoza. But when you talk about retrofitting or rehabilitation, there is this supplemental, I would say supplemental. Any problem? Am I clear? Okay. So FEMA 273, wherein you have these NERF guidelines for the seismic rehabilitation of buildings. Then later on, we have ASCE 31-03 on seismic evaluation of existing buildings. Then that is supplemented with ASCE 41-06 on rehabilitation of existing buildings. Then, of course, an updated version of that is 41-13. Now the latest version is 41-17. So this, the 3103 and the 4106 were combined into one document, and you have this 4113 or the latest 4117 for the difference or for the evaluation and retrofit design of buildings. Of course, this was presented by Doc Mac, the IEBC, no, as an alternative. And you can search to these links, these website links on some California existing building code and these FEMA publications on FEMA publication on seismic rehabilitation. Okay, let me just, I'm not the last part of my presentation. Just quickly, let me show you this case study. This is actually our project, no, in the office wherein we are to evaluate an existing building. You have this configuration. The plan is shown here. You have these buildings, which is very irregular, no, and then this is the frame. Of course, what you see here are some sort of a retrofitted or rather strengthened frame model. So we did first structural investigation. We do site inspection. We do field measurement. We prepared the as found, not the as built, because this building is I think in the 60s and the 70s, and there's no more as built. So if there is an available as-built, then you validate. Then if there is none, then you have to prepare the as-found. Then you do the testing, no? Because you cannot do the as-found without conducting all this testing. You have to do the probing of the foundation. You have to expose the foundation so that you'll know what's the size of the footing, what foundation type is used. Then you do rebound hammer test. Correlated with the coring test. We do the rebar scanning so that we'll be able to know the amount of reinforcement when we have to validate that using chipping works to validate your rebar scanning. And then we have to do rebar extraction for us to get the strength of the steel. And then we have to conduct a UPV if we have seen some cracks. And then definitely you have to do additional or you know, if this building was built in the 60s, you do not know what has happened underneath, then you have to perform geotechnical investigation. So then after that, we do the structural analysis, and if warranted, then we do the retrofit design. Now, basically, as per terms of reference of the project, the code that we are required to use is the NSCP 2015. So we did the analysis, the linear analysis, based on the NSCP 2015. Now, we do the assessment on the structural adequacy of the members, so we do the demand to capacity analysis. Then we have to come up all components with the DZR ratios, and then we'll be able to identify how are we going to retrofit the or rather to strengthen the structure. And then we prepare a retrofitting solutions. As I have said a while ago, 3 schemes is required if necessary. I mean, the retrofitting itself is necessary. So this is now the first scheme as a building frame wherein we add braces to resist the lateral forces. That is the scheme 1. Then the second scheme as a dual system wherein we provided shear walls. So you will see the shear walls in this direction and the shear walls in this direction. And then the third scheme we presented is retaining it as a special moment resisting frame, because the existing building is supposed to be an SMRF system. Then the strengthening is local members, no, doing the jacketing. It's a combination of concrete jacketing, steel jacketing, and fiber wrapping. And we came up with the 4th scheme. Although we are required only to do 3 schemes, but you know, presenting the 3 schemes, you have to present, no, what are the which among the 3 schemes would be advantageous to the client, no, in terms of the cost. So I will not, of course, discuss anymore the details of that, but in that presentation, in this particular project, it was the scheme 1 that we first recommended, wherein the cost of that is, of course, that scheme 1 give us the least cost among the 3, no? So the bracing itself, rather than using the scheme 2, wherein we provide shear wall and then we or do the jacketing. Now in the 4th scheme, what we did is the global retrofit using vibration control. And in this case, we use dampers. And let me show you, no, because this is very interesting. I will show you a video because I cannot upload the video in that because it's too large. So let me just show you that video. Okay, hold on. Okay. So this is the video of that building. On the left side, do you see the video? I hope you see the screen. On the left side of the screen, that is the model of the structure without the dampers. On the right side, that is the model of the structure, which is in which the dampers are already installed. So this is subjected to a ground motion, actually 6 ground motions, and 3 are synthetic, and the other 3 are real earthquake events. And this is now the retrofitting scheme here is in that direction, in the transverse direction. The shear walls were provided as wing walls. In the X direction or in the translational direction. So you could just imagine if that building is subjected to this ground motion, no, on the left side, no, it seems that the building will collapse, no, will not be able to sustain that ground motion. But if you have that shear walls added as wing walls to the building, then the building would still be there. Now, let me show you the other video. Now this one, okay, this one is the earthquake in the longitudinal direction. Now, okay, in sorry. Okay, this one, the earthquake is in the longitudinal direction. Now, in the longitudinal direction, the dampers are installed. So, predominantly, the dampers there are the one resisting the seismic demand. So, you can see the response of the behavior of the building or the response of the building when subjected to this ground motion. So, as you can see, the movement or the deformation of the building on the left side is very significant to the point that in that direction there is more likely that the building will not be able to sustain the ground shaking. So in conclusion, traditional member retrofitting techniques such as jacketing and post-tensioning would be economical in terms of material cost. However, other construction factors could be costly, such as labor, time, and equipment. You know, in the case study that I have presented, the main issue there, the reason why we came up with the scheme 4, because of the disruption of operations of that building. That is an office building, a government building, where you cannot where you cannot simply disrupt the operations because it is a vital government agency building, and 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 the cost of relocating the occupants of the building would be additional cost to the first scheme. Global retrofitting may be considered as a better alternative if the primary objective is to reduce seismic demand in the structure and increase the seismic resistance of the structure. Retrofitting and strengthening may be considered as the most suitable strategy for sustainable development. So let me just acknowledge, uh, of course, these are the references which I use in my presentation. Now let me just acknowledge in the red, in the red highlights of my this reference here. Some photos and excerpts in presentation materials were used from Kawakin, Freycinet, Engineer Ronaldo Ison, Engineer Woody Cobardo, Engineer Wilfredo Lopez, Engineer Dr. Andres Winston Oreta, and Dr. Fernando Herman. So with that, thank you for watching and listening. Now open to Q&A. Thank you very much.
Hi, Adam.
Hello.
Yes, there are only a few questions now.
Okay.
In the process, there are many questions that come out, but maybe in the course of your presentation, they get the answer, so they just dismiss the
Yeah.
questions. And some clarificatory questions, I've already typed the answer because we're running out of time. And the
Okay.
most common question is, what is the liability of the engineer who does the retrofitting design?
Okay.
So there's a question that if ever the owner wishes to change loading, for example, and there's a need to retrofit, who will be then the engineer of record after the retrofit, and what is the liability of the retrofitting engineer?
Okay. If well, definitely, no, when you do the evaluation and then you do eventually the retrofitting, now since you are the last touch on the structure, then the professional liability will be transferred to you. Say for example, an existing building, then there is an additional floor as required by the client. That obviously the client will hire you to evaluate and do some strengthening if needed, since there would be a change in the use of the building or increasing the number of floors. Now, since you are the one doing the design, and then the design was implemented as a retrofitting, then the responsibility will be transferred to you. And it will start again, no, for a 15-year liability as per our revised penal code. So if
Okay, so
the engineer of record before, no, wala na, no? Mawawala na yung responsibility kasi ikaw na yung nag-handle nung structure eh. So that means you really have to be very careful in doing this kind of structural design.
and of course, you just don't sign a certification for a building that you did not analyze. That is just
Exactly.
criminal.
That is correct. Do not issue certification that you have not performed a diligent due diligence audit of your structure, detailed evaluation, and retrofitting.
Okay, there's a question about the particular item about your design using the CHB. Sir Adam, if I were to model or not to model the CHB wall as a strat member, how should my CHB wall to column beam connection look like for both cases? I think this is very
Okay.
particular for how you design it.
Yeah, actually, that is a very good question. No? Although I have been mentioned it that most engineers, no, if you are designing a moment frame, no, although we know for a fact that when constructed there would be these infill walls. So it's only a matter of that these infill walls should not be contributing stiffness to the structure. So make sure of that. So that means you have to look at the connection. You have to provide a gap, no, when between the walls and that of the surrounding frame, the columns and the beam. So the connection is the key there. If in case you model your structure as a purely concrete frame, but if you can still do the modeling, but in this case you have to model the infill wall as struts so that it will have contribution to the entire structure when you subject to the lateral forces. But it's all up to the designer. Now, I would like to think that most, no, I will say almost all designers, all structural engineers do the moment frame modeling as some purely moment frame.
Okay, so there's one cute question here. By how much percentage of inclination will you recommend or require a building to be demolished, considering that there are no cracks or any deformations observed on the subject building except for the inclination and the discomfort observed by the occupants?
Okay.
Leaning Tower of Pisa?
Actually, that's a very good, tricky question. Now, if there is already a perceived or observed inclination of the structure, you can model it in a way that you have to induce the deformation in your modeling or that deformation so that you will know whether the structure is still okay. So if ever that the structure will still be okay, considering that you do not find any cracks or this sign of distress in the structure, then definitely you can still restore that building and then provide necessary retrofitting or strengthening so that the structure will still be there even if it is inclined. So like the Tower of Pisa.
Okay, so I think we need to do another set of
Assessment.
seminar, online seminar for those other questions like the ones
Yeah.
interested about base isolators and other guidelines on the design parameters that we need to discuss. Yeah, there are a lot of questions, but those are some questions are not very related to the topics being discussed.
Oh, yeah.
Okay, so
That
there's
means we
one.
would have
I
to
think
come up with
this one
follow-up
is timely.
seminar.
Are we ready for the big one? Are there any programs being done by ASEP to spread awareness to the Filipinos about this scenario? Blah, blah, blah. Would you like to
Oh,
answer that?
you know, yeah, thank you, Janet. This is a free webinar, and then we came up with this idea of discussing about evaluation and retrofitting of existing structures because definitely ASEP CPD will be coming up with a more detailed discussion on this one. Kumbaga, this is only a teaser. So just to to get the interest of almost everyone and try to understand that there is a solution to some to those this kind of problems, no? Especially if you talk about if we can restore the existing buildings, how can we improve the existing building and so on. Definitely we will be coming up with a series, no? But this time it won't be free webinar, but a minimal fee, no, for these webinars in the future, because our mission, no, the mission of the ASEP is really to make almost all most Filipino structural engineers to be competent enough, no, knowledgeable enough to understand all these technology in and development in evaluating and retrofitting existing structures.
Okay, I think that's all for the questions they raised. Those remaining questions were partly or in a way answered by your presentation and the previous answers. So I think we really need to do another set of pre-seminars for basic design, no? And there
Yeah,
are
yeah, yeah.
very
Sure,
elementary
sure.
questions being raised, not part of retrofitting. So since
Yeah.
we have no more quality time to spend, I'll bring back the floor to Leo. Leo, take it over.
Hello, thank
Adam, for
you.
the